The universe is getting bigger right now. Right this second, as you're reading this, the universe is expanding. Not just growing, but accelerating outward at speeds that would make your head spin. Every galaxy beyond our cosmic neighborhood is racing away from us, and the farther away they are, the faster they're moving. We're talking about galaxies zooming away at speeds of millions of kilometers per hour. And here's the kicker. They're not actually moving through space at all. Space itself is stretching like cosmic taffy, carrying everything with it. Neil deGrasse Tyson captured this in his book, Welcome to the Universe, when he wrote that the cosmos ends not with a bang, but with a whimper. That simple phrase tells us everything we need to know about where we're headed, and it's both terrifying and fascinating at the same time. Edwin Hubble made this discovery back in the 1920s when he noticed something peculiar. Every galaxy he observed was moving away from us, and the relationship was perfectly predictable. The farther the galaxy, the faster it receded. This became known as Hubble's Law, and it fundamentally changed how we understood our place in the cosmos. Suddenly, the universe wasn't this static, unchanging backdrop. It was dynamic, alive, and constantly evolving. Think of it like baking raisin bread. As the dough rises, every raisin moves away from every other raisin. If you were a tiny observer sitting on one of those raisins, you'd swear that you were at the center of the expansion because everything else would be moving away from you. But here's the thing. Every single raisin sees the same pattern. The dough is space, and we're all raisins, watching as the distance between us grows larger with every passing moment. How fast is this thing expanding anyway? Scientists measure the expansion rate using something called the Hubble constant, which sounds like it should be constant, but actually changes over time. Currently, measurements suggest a rate of around 74 kilometers per second per megaparsec. What does that mean in English? For every 3.3 million light years of distance, objects appear to be moving away from us an additional 74 kilometers per second faster. So a galaxy 1 megaparsec away recedes at 74 kilometers per second, while 2 megaparsecs away races off at 148 kilometers per second. Now here's where it gets controversial. Different methods of measuring this expansion rate give us different answers, and scientists are scratching their heads trying to figure out why. Observations of the early universe using the Planck satellite predict an expansion rate of about 67 kilometers per second per megaparsec, while measurements using nearby galaxies and supernovae suggest it's closer to 74. That 9% difference might not sound like much, but in cosmology, it's huge. It suggests we might be missing something fundamental about how the universe works. If you're enjoying this deep dive into the cosmos and want to stay updated on the latest space discoveries and cosmic mysteries, hit that subscribe button and turn on notifications so you never miss an upload. What's actually driving this expansion? For decades after Hubble's discovery, astronomers assumed that gravity would eventually slow down the expansion. It made sense. All that matter pulling on all that other matter should act like a cosmic brake, right? But in the late 1990s, two independent teams studying distant supernovae made a shocking discovery. The expansion wasn't slowing down at all. It was speeding up, and the teams responsible for this discovery won the 2011 Nobel Prize in Physics. The culprit? Something called dark energy, and it makes up roughly 68% of everything in the universe. We can't see it, we can't touch it, and we barely understand it, but it's pushing the universe apart with increasing strength. Charles Liu, the astrophysicist who co-wrote One Universe at Home in the Cosmos with Neil deGrasse Tyson, has spent years studying galaxy evolution and the expansion history of the universe. His research helps us understand how galaxies formed and evolved in this expanding cosmic ocean. Dark energy behaves unlike anything else we've encountered. Normal matter and radiation get less dense as the universe expands, but dark energy maintains a constant density. As space expands, it fills with more of this energy of space, which fuels the universe's expansion even more. It's like a cosmic feedback loop that never stops. The Big Rip, when the universe tears itself apart. And now we get to the really disturbing part. Neil deGrasse Tyson described this scenario during an interview with Stephen Colbert, explaining what keeps him up at night. He called it the Big Rip, where the accelerating expansion will eventually outstrip all gravitational forces currently holding things together, eventually overcoming molecular bonds that hold your flesh together, then ripping your atoms apart, and finally separating the very fabric of space and time itself. Let that sink in for a moment. We're not talking about things just drifting apart. We're talking about the universe becoming so violently expansive that gravity itself becomes meaningless. First, galaxy clusters would be ripped apart, then individual galaxies, then solar systems, then planets, then you and me and every atom in our bodies. If this phantom energy scenario plays out with an equation of state parameter of -1.5 and a Hubble constant of 70 kilometers per second per megaparsec, the time remaining before the Big Rip would be around 22 billion years. That sounds like forever, and it is. Our sun will die long before the Big Rip becomes a problem. But on cosmic timescales, 22 billion years is just a blink. Stick around because we're about to explore the alternative fate of the universe, one that's equally mind-bending but plays out on an even longer timescale. The Big Freeze, a slower but equally final death. The Big Rip is actually less likely than another scenario called the Big Freeze or heat death. This is the fate most scientists think awaits us, and in some ways it's even more unsettling because it's so gradual and inevitable. The heat death of the universe posits that the universe will evolve to a state of no thermodynamic free energy, and having reached maximum entropy, will be unable to sustain any further thermodynamic processes. In simpler terms, everything will eventually become the same temperature. And when that happens, nothing can happen anymore. No stars can shine. No planets can form. No life can exist. The universe becomes a vast, cold, dark graveyard. Here's how it plays out. Stars will continue forming for the next trillion years or so, burning through the available hydrogen and helium. But eventually, the raw materials run out. The last stars will flicker out, leaving behind only dead remnants, white dwarfs, neutron stars, and black holes. These objects will slowly drift apart as the expansion continues. Even black holes won't last forever. Through a process called Hawking radiation, even supermassive black holes will eventually evaporate over timescales of 10 to the 100 years. After that, the universe enters what's called the dark era, consisting mostly of a thin gas of photons and fundamental particles, all spread across incomprehensible distances. Why the Hubble constant is decreasing, but the universe is still accelerating. This confuses a lot of people, so let's clear it up. The Hubble constant, which measures the expansion rate, is actually decreasing over time, but the universe is still accelerating. How does that work? The key is understanding what acceleration means in this context. The Hubble parameter isn't simply the rate of expansion. It's the derivative of the scale factor divided by the scale factor itself. What this means is that even though the Hubble parameter is dropping, the actual velocity at which distant galaxies recede from us is increasing because they're getting farther away. If you measure a galaxy's velocity today and come back a billion years later to measure the same galaxy, it will be moving away from you faster, even though the Hubble parameter has decreased. That's acceleration. The galaxy itself is speeding up in its recession, even as the overall expansion rate gradually drops. Dark energy keeps the Hubble parameter from dropping to zero. Without it, gravity would eventually win, and the expansion would slow dramatically or even reverse. But with dark energy, the expansion rate is asymptoting to a final value that's only about 30% lower than its current value, meaning the universe will keep expanding forever, just at a gradually stabilizing rate. The mysterious nature of dark energy. We still don't really know what dark energy is. Einstein actually predicted something like it back in 1917 when he introduced the cosmological constant, a repulsive force that would balance gravity and keep the universe static. When Hubble discovered the universe was expanding, Einstein abandoned the idea, supposedly calling it his greatest mistake. But now it's back with a vengeance. The simplest explanation is that dark energy is a property of space itself, a kind of vacuum energy that exists everywhere at all times. This fits with what we call the cosmological constant, where dark energy has an equation of state parameter of exactly -1. Recent measurements narrow the possibilities for dark energy and are consistent with the simplest interpretation that it's mathematically equivalent to Einstein's cosmological constant. But there are alternatives. Maybe dark energy is actually a dynamic field that changes over time, getting stronger or weaker depending on the era of the universe. Recent results from the Dark Energy Spectroscopic Instrument collaboration suggest evidence that the density of dark energy might be slowly decreasing with time, though this evidence isn't conclusive yet and requires further verification. When will our local neighborhood feel the effects? You might be wondering, if space is expanding everywhere, why isn't the distance between Earth and the Sun increasing? Why aren't we getting ripped apart right now? The answer has to do with gravity on local scales. The expansion of the universe only dominates on very large scales, where gravity is weak. Within our solar system, within our galaxy, even within our local group of galaxies, gravity is strong enough to hold things together. These structures are gravitationally bound, meaning they're immune to the cosmic expansion. But galaxies beyond our local group, those are receding. About 5 billion years ago, dark energy became the dominant force in cosmic expansion. Any galaxy that wasn't gravitationally bound to us by that point is now accelerating away, and will eventually lose sight of them as they cross beyond our cosmic horizon. The controversial debate about the universe's isotropy. Here's something that might surprise you even more. We've always assumed the universe expands the same way in all directions, a principle called isotropy. But recent observations have raised questions about this fundamental assumption. Studies of galaxy clusters using X-ray observations from Chandra and XMM Newton suggest the universe might be expanding at different rates in different directions. If true, this would revolutionize cosmology. It would be like discovering the yeast in our cosmic bread wasn't evenly mixed, causing the dough to rise faster in some places than others. Most scientists remain skeptical of these findings, arguing that more evidence is needed before we overturn one of the fundamental pillars of cosmology. But it's exactly this kind of controversial observation that drives science forward. We question, we test, we refine our understanding. What this all means for the fate of the universe. So, where does this leave us? Charles Liu's work on galaxy evolution and the star formation history of the universe helps us understand how we got here, but it also informs predictions about where we're going. His research focuses on colliding galaxies, active galactic nuclei, and the star formation history of the universe, giving us crucial insights into how cosmic structures formed and how they'll eventually fade away. The universe is heading toward one of 3 possible fates. The Big Rip, where dark energy becomes so strong it tears everything apart. The Big Freeze, where expansion continues forever, and the universe slowly fades into cold darkness. Or potentially something we haven't even imagined yet, some twist in the nature of dark energy that changes everything. Right now, all evidence points toward the Big Freeze. The heat death scenario has gained ground as the most likely fate, with the universe destined to expand forever, growing colder and darker until nothing remains but the faintest whisper of radiation spread across infinite space. Neil deGrasse Tyson's words echo across cosmic timescales. Not with a bang, but with a whimper. The universe won't end in some spectacular explosion. It will simply fade away, slowly and inexorably, until there's nothing left but cold, empty space stretching in all directions forever. The expansion of the universe is one of the most profound discoveries in human history. It tells us we live in a dynamic cosmos, one with a beginning and an end, one where nothing stays the same. Every moment, space grows larger. Every moment, distant galaxies race farther away. And every moment, we move closer to an ending that plays out on timescales so vast they make our entire species' existence seem like a fleeting instant. But here's the beautiful part. We get to be here now, in this cosmic moment, able to understand what's happening and appreciate the sheer grandeur of it all. We're made of atoms, forged in stars, living on a planet orbiting an average star in a galaxy that's one of hundreds of billions, all racing apart in an accelerating expansion. We're only beginning to understand. If you found this exploration of the universe's expansion fascinating, Don't forget to subscribe to the channel. Hit that bell icon so you're notified whenever we dive into another cosmic mystery. The universe is vast, strange, and absolutely incredible, and we're just getting started exploring its secrets. Thanks for watching, and keep looking up.